Welcome back to the ARSET training, Building Climate Risk Assessments from Local Vulnerability and Exposure. My name is Sean McCartney, and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the second and final part of this two-part webinar series. The following slides provide an overview of the two-part webinar series. So, why is climate risk assessment important? Climate change impacts and risks are becoming increasingly complex and more difficult to manage. Climate change impacts on infrastructure also vary by region. By identifying at-risk assets and the type of climate conditions that drive problematic responses, stakeholders and scientists can co-develop risk information to suitably address those risks. By following the approaches described in this two-part training, participants will be able to recognize the dramatic contextual nature of climate risk assessments and adaptation planning, identify components of their own system that are vulnerable or exposed to climate risks, work with stakeholders to construct climate risk information that is useful for their decision-making processes, and use risk information to identify adaptation strategies for implementation. The prerequisites for this two-part training are the fundamentals of remote sensing, introduction to NASA resources for climate change applications, and selecting climate change projection sets for mitigation, adaptation, and risk management applications. Links to each of these trainings are provided, and we encourage you to go through them to familiarize yourselves with content related to this training. Over these 2 days, there will be two 1.5-hour sessions, which will include presentations and question and answer sessions. All materials and recordings from each session will be made available on the training webpage. Part 2 is focused on developing climate adaptation support for NASA centers. There will be one homework assignment which is already posted on the training page with a due date of October 5th. A certificate of completion will be awarded to those who attend all live sessions and complete the homework assignment before the given due date. The objectives for the second part of the webinar series are as follows. By the end of part 2, participants will be able to identify how adaptation decision support theory is applied in practice and deepen familiarity with NASA resources and methodologies. Please place your questions in the questions box and we will address them in the order that we received at the end of the webinar. Feel free to enter your questions as we go. We will try to address all questions during the question and answer session after the webinar. The remainder of the questions will be answered in the Q&A doc, which will be posted to the training website about 1 week after the training. It is now my pleasure to reintroduce the guest trainers for today's webinar, Dr. Alex Ruane and Sanketa Kadam. Alex is a research physical scientist at the NASA Goddard Institute for Space Studies, where he is a co-director of the GISS Climate Impacts Group and an adjunct associate research scientist at Columbia University, Center for Climate Systems Research in New York City. Alex serves as a research coordinator and climate team leader for the Agricultural Model Intercomparison and Improvement Project, an international transdisciplinary project connecting climate science, crop modeling, and economic modeling to place regional agricultural impacts of climate change into their global economic context to assess uncertainties, vulnerability, and world food security both today and in the future. Alex served as a coordinating lead author for the Intergovernmental Panel on Climate Change 6th Assessment Report, Working Group 1, Chapter 12, Climate Information for Regional Impact and for Risk Assessment. Alex's research uses a variety of climate and impacts assessment models to examine the influence of climate variability and change on a variety of sectors, including agriculture, water resources, urban areas, infrastructure, energy, and human health, leading to the development of adaptation strategies and decision support tools for stakeholders and policymakers who need to understand vulnerabilities and uncertainties to successfully manage risk. Sanketa is a PhD student in the Department of Earth and Environmental Sciences at Columbia University in New York City. She's also part of the research staff at NASA Goddard Institute for Space Studies with the Climate Impacts Group. We are delighted to have them joining us as guest trainers. Alex, over to you.
Thanks, Sean. Once again, my name is Alex Ruane, and it is my pleasure today to present part 2 of our ARSET training. This one will be focusing on developing climate adaptation support for NASA centers, where we will apply some of the lessons and approaches developed in part 1 on how we do climate risk assessment that is driven by the demand from stakeholders, so that the climate risk assessment can more directly inform decisions and adaptation and various other types of related planning. I'm joined today by Sanketa Kadam, who is also with me at the NASA Goddard Institute for Space Studies, and we'll tell you a little bit more about the NASA project that we're going to be describing now.
Thanks, Alex. So let's do a quick refresher to what the CASI initiative is all about. The Climate Adaptation Science Investigators Initiative spans the entire USA, covering about 14 centers and facilities. The program tackles the question of what climate threats to NASA facilities are and how we can prepare for future challenges. It does so through its mission of providing latest scientific research on climate change to help NASA facility managers adapt to increasing climate risks. It's a collaboration between NASA scientists and managers to co-generate key current and future risk information to help protect operations, assets, workforce throughout the agency. Please note that CASI 2 is an ongoing initiative. We will present preliminary results in this presentation, and a more formal report is planned for late 2023 and 2024. To really understand the nature of climate risks at NASA centers, let's consider the Bobcat fire in Los Angeles County. In this case, the risk was not the fire itself, but smoke that affected JPL operations over the course of a week in 2020. The growth and spread of this fire was particularly sensitive to the daily progression of what we call the vapor pressure deficit, or VPD. This example shows how we need to consider a variety of meteorological conditions, both at and around centers, given complex climate hazards and the risk of indirect impacts.
As a reminder of the climate risk assessment methodology that we use in part 1 of this ARSET training and that we apply in the CASI project, there are 5 different phases of our climate risk assessment that help us ensure that the climate information we use is driven by stakeholder demand and useful for stakeholder decisions. The first phase is the identify phase, where we identify the system of interest and the stakeholders and their roles in decision making. The develop phase helps us ensure that our climate information is sensitive to the specific context of the systems and the assets that are at risk, and helps us understand how we can place our climate into the specific setting of decision making. The evaluate phase looks at different components of risk, including hazard, exposure, and vulnerability, and brings that from a general set of climate information to specific climate factors that can be linked to specific risks. We then assess the magnitude and frequency and other components of impacts using a variety of diagnostics and models so that we can understand the growing concerns as well as uncertainties in the overall risk assessment. The final phase is to identify specific interventions, the scales at which interventions may be implemented, and then to monitor the overall set of implementations and to see how well they are progressing against their own design criteria and the climate changes that are occurring. For more on how this works in the CASI project, back to Sanketa.
Thanks, Alex. So we'll be looking at the phase 1 or step 1 of our assessment, which is the identify phase. We will be relating theory to practical examples through the CASI initiative. Next slide. And we began doing that by mapping out and identifying stakeholders for CASI through a series of conversations with the Office of Strategic Infrastructure, or OSI, who are really our primary stakeholders. OSI manages the infrastructure at NASA where decisions are made at different time horizons. And as you can see, there are 3 divisions that really CASI interacts with under OSI. This is the Facilities Real Estate Division, the Logistics Management, and the Environmental Management Division. For example, through the decisions made by Facilities Real Estate Division, they could be both on short-term and long-term scale in terms of building restoration project versus scoping out new building development. CASI also responds directly to the executive order to ensure that federal agencies develop and implement climate adaptation plans. Our primary stakeholders are division directors managing these at both the headquarters level, but also master planners, energy managers, and environmental managers at different centers who work under these divisions. These managers connect headquarters allocations, priorities, and budgets to center operations. So looking at one division here of facilities and real estate, and under that we have the master planning division, which CASI has identified as the main entry point into connecting with other center managers and divisions. And this is because master planners work with operations like energy systems, stormwater systems, workforce, and real estate management, and deal with both immediate decision making and longer term decisions over about 20 to 50 years of span. CASI climate observations and products really feed into the climate action plan, center resilience, and agency resilience plans, which are both agency-wide and at the center level, that then identifies responses into the agency master plan, the agency capital investment program plan, and the center master plans. So NASA has partnered with National Renewable Energy Laboratory, or NREL, to conduct regular resilience assessments at centers and at an agency level. That includes vulnerability and exposure assessments. And CASI initiative connects to these ongoing assessments by providing climate expertise from our scientists to help build an overall NREL risk profile that includes earthquakes, technological accidents, and social unrest. NREL makes these risk reduction investment recommendations to the center, which covers the overall risk profile. We mentioned that CASI is a collaboration between scientists and managers. These scientists form the backbone of scientific assessment, ensuring that we have the most reliable and up-to-date information. Their unique scientific expertise allows us to make more accurate predictions and decisions, which is invaluable for both planning and crisis management. With established relationships with local leadership and workforce, these scientists are well positioned to communicate findings effectively and implement solutions promptly. These experts understand the center's culture and day-to-day experiences, allowing them to tailor their assessments and recommendations specifically to a center's needs. And the scientists are supported by NASA's Earth Science Divisions, which is the ESD, and they have access to cutting-edge research, technology, and NASA's resources. During CASI's initial setup, we considered additional partners such as academic institutions, industry leaders, that contribute to the breadth and depth of our assessment. There is somewhat a blurry line between partners and stakeholders in our work. The CASI results have multiple uses ranging from public policy to other center applications. The NREL is not just a partner, but also a user. They're helping us develop our products, but they also plan to use some of the CASI products in their own resilience assessments. All of these different parts and the whole center teams come together to meet the OSI's mandate and priorities on identifying investments in future infrastructure. And through this, it's essential to understand their day-to-day workflow and decision scopes, with answering questions like what is practical flexibility in the budget, what command structure is available on decisions, and what metrics and time horizons are used to measure success in the project. This really helped CASI determine the planning and development structure of the overall project. All of this fed into identifying the sector problem and system scale for CASI. At an agency level, the priorities and budget allocations are longer term, like scoping out new properties, new constructions, whereas at center scale, the challenges are cross-cutting between departments. Infrastructurally, these challenges within a center also have different spatial and temporal scales. Plus, different centers in different locations have diverse priorities. A building infrastructure project has a different temporal priorities versus an ecosystem rehabilitation project. So that was a step one or phase one of identify in the CASI initiative. The step two in our risk assessment is develop. Our goal in CASI is to develop context-specific analysis and products that are targeted and relevant to decision support. And one of the ways we achieve this is by combining bottom-up and top-down approaches in identifying challenges. We engage with the center managers to help organize center-to-center resilience, as well as NASA headquarters to help develop an agency-wide perspective to risk. Our focus has always been in developing an inclusive process of engagement. The science team members of CASI leverage their expertise to build local trust around the centers and provide valuable contextual insights. Similarly, the division heads help allocate resources. Master planners ensure the project objectives align with the overall organizational goals. The CASI leadership at GIS focuses on developing scientific protocols so that we maintain consistency throughout the centers and throughout our science team. And this helps creating a cohesive understanding when we synthesize findings across the centers. We also manage stakeholder relationships. The OSI leadership works with GIS leadership to ensure overarching organizational objectives are met of the agency. To foster continued and sustained collaboration, CASI developed a comprehensive communication plan, which includes timely meetings among the project science team to discuss project progress, challenges, next steps, and to manage relationships with stakeholders. Center by center communication meetings are scheduled on a monthly basis, where information is disseminated to keep all parties informed of updates and key decisions. The plan also emphasizes on a co-development of sustained engagement process by developing intermediate meetings between stakeholders and work group scientists that may require deeper discussions depending on the hazard they want to focus on. To facilitate seamless data sharing, CASI established clear protocols for data access with center managers and headquarters. Finally, the dissemination of findings and updates will be executed through a multi-channel approach, which is including reports, meetings, emails, etc. To create decision-relevant products, CASI developed several survey-like questions for stakeholders to understand the decision-making process. In this phase of develop, we really wanted to focus on usability of the information that we are producing. And so this is an example of some of the questions that we developed to ensure that we have effective communication with our stakeholders.
The next phase of the project is the evaluate phase. And within CASI, we use this climatic impact driver framework to organize the way we approach climate risk information. Looking first at these top major types of climatic information or of climatic impact drivers, you'll see that we needed to represent different types of climate conditions and climate extremes. This is especially important because the situation and the context of each center calls for different types of information. The Western centers in particular expressed a need for information on drought and wildfires. Coastal centers had immediate need for information on sea level rise and coastal flooding. Launch facilities indicated a need for information on severe wind speeds. And there was a broad interest in heavy precipitation and pluvial flooding and extreme heat across all of the different centers. This motivated CASI to develop different work groups that focus on different parts of the climate change question. We developed a work group on sea level rise and coastal flooding, on extreme weather events, on fires and air quality, on energy, and on water budgets. Each of these took on different climatic impact drivers and identified different types of metrics that were useful for decision processes in each of these areas. As we're thinking about the type of climate information that was needed, we had to evaluate the climate projection needs. In general, we looked for information that was at fine resolution because we know that there are high resolution features, small spatial scales that are important at each center. And you must remember that the centers are very small compared to the typical climate model grid cell, which can be 20 or even 100 kilometers wide. We wanted information that was bias adjusted to ensure that the observed features are well represented below that larger grid scale. We wanted to use the latest climate model outputs from the 6th phase of the Coupled Model Intercomparison Project, CMIP6, to ensure that we are using the best and latest model outputs. We wanted to use multiple emission scenarios to give stakeholders a range of plausible futures that they could prepare for, recognizing that the policy pathways that we will take are beyond the scope of what CASI themselves can decide. We also wanted to use multiple climate models so that we can understand the larger messages that arise from multi-model means and other ensemble statistics, which have proven to be, in many cases, more useful than selecting a subset of, or a small subset of models. We have also wanted to distinguish that ensemble using some physical mechanisms to exclude hot models, so our projections do not have a hot bias. We're going to talk more about what that means, but the fundamental idea is we want to use our physical intuition and our understanding of strengths and weaknesses of the models to make sure that we are not including models that may bias our results. We are also interested in models that allow us, or in projection sets that allow us to access a high number of climate variables, because we have this breadth of climatic impact drivers and we need climate projection data for all types of climate change risks. After considering all of these different aspects and characteristics that we want in a climate projection set, we were drawn to the NASA Earth Exchange Global Daily Downscale Projections, or the NASA Next GDDP dataset. NASA Next GDDP offers 35 general circulation models or climate models from CMIP6, which is the latest iteration of climate models. You can see in the upper right the resolution of these types of simulations, and here we're looking at the year in which the local temperature change exceeds 2 degrees Celsius compared to the 1950 to 1979 period. Under a high emissions SSP 5-8.5 scenario. This gives you an idea of the coverage and the variables that we're interested in are largely present in the next data set. These include the minimum, maximum, and average daily surface temperatures, precipitation, relative humidity, specific humidity, downwelling, long wave and short wave radiation, and surface wind speed. Within the next ensemble of climate models, we selected a subset that was based on our physical understanding of the climate system's response to greenhouse gas forcing. A common metric for this is something called the equilibrium climate sensitivity, which is the steady state rise in surface temperature averaged across the whole globe following a doubling of the atmospheric carbon dioxide concentration from pre-industrial conditions. This ECS metric is well known in the physical climate community and gives you a fundamental idea of how fast the world warms to the greenhouse gas emissions that society is currently putting into the atmosphere. The models that tend to warm up more rapidly than the others are sometimes deemed hot models. But even more importantly, what we do is we filter this by the Intergovernmental Panel on Climate Change assessment of what the very likely range for equilibrium climate sensitivity should be. And that ranges between 2 and 5 degrees Celsius. This represents uncertainty in the physical climate system that is captured by this range across the climate models. But when there are models that have an equilibrium climate sensitivity above 5 degrees, or on the flip side, a few below 2 degrees, which warm up too slowly compared to observations and other constraints that we've seen in our observational system, these models are outside the assessed range of the IPCC, and we therefore are cautious of them in the CASI project. There's a second metric we also look at called the transient climate response, which is more about the non-equilibrium year-by-year progression of warming to a steady or a steadily increasing amount of greenhouse gases. You can see here defined as the warming rate when you have a 1% increase year over year in atmospheric CO2 concentrations. And what we see here is that the transient climate response was assessed by the IPCC to be between 1.2 and 2.4 degrees Celsius. So this gives us two metrics about the overall equilibrium change and the transient change in response to greenhouse gases. And when we apply these filters, we end up with a smaller set of the NASA NEXT models that give us a more likely and strongly backed by observations set of models in terms of how the overall climate system responds to climate change. When we take the full NASA NEXT subset and compare it to a smaller subset where we have filtered by this transient climate response, you can see that we do a much better job of sticking with the historical and assessed warming according to the IPCC. So each of these little gray wiggles here represents a different climate model. And the blue line here is the historical warming and the assessed warming done by the IPCC through an assessment of a broad base of literature and observations. If we take all of the models without distinguishing between these models and the hot models, you would follow this black line as an ensemble average. But if we do a subset according to the IPCC range, we follow this light blue line, which sticks much more closely to the historical and assessed warming. So this gives us a strong impression that the models that we have selected are doing a good job of representing the current state of climate physics understanding in the community. In applying the NASA NEXT GDDP projections, we sample from different emission scenarios that represent different pathways of societal economic growth, technological use, land use, and other aspects that will determine the greenhouse gases and other exchanges related to the climate system over the coming century. The IPCC characterized scenarios as low, intermediate, and high, corresponding to the SSP 1-2.6, the SSP 2-4.5, and the SSP 3-7.0 scenarios. You can see these scenarios on the right side of the screen. Notice that we do not look at what the IPCC characterized as the very high scenario, which is the SSP 5-8.5, because that one is increasingly disconnected with the current trends in coal use and other aspects in society that have increasingly focused the climate science community on these other scenarios. For more information on these scenarios, you can see the previous ARSET training around selecting climate projection sets. Within CASI, we look at timescales from the 2020s out to 2100. Next GDDP allows us to get to a spatial scale of about 27 kilometers. And you can see in a few slides some other data sets that we are using to augment, including the NEXT LOCA data set and the Land Information System, which we will describe in future slides. We take outputs from all of the models, but then we look at a set of projections focusing on 22 models that allow us to avoid the hot model situation. So these 22 models are the central core of our NEXT based projections. We also deliver results using maps, tables, and data that are tailored for the NASA centers and oriented towards the type of things that stakeholders have interest in as they're making resilience decisions. Within CASI, we have linked a lot of our analyses to the NASA Land Information System. which allows us to provide higher resolution and elaborated hydrological variables beyond what NASA Next GDDP natively provides. For those who don't know NASA LIS, the Land Information System is a system for uncoupled and coupled land modeling and data assimilation. It uses multiple land surface models and can integrate satellite, ground, and reanalysis data in the historical period for a comprehensive data assimilation infrastructure. It also allows us to connect with high performance support for fine resolution and ensemble modeling. So we have taken the LIS system and elaborated the next GDDP outputs, which gets us further variables and allows us to downscale all the way down to about 1 kilometer resolution across all 22 GCMs and the 3 emission scenarios, the low, intermediate, and high. This gives us more information so we could augment our analyses of extreme events, especially at the land surface, and gives us access to more information around hydrological cycle and water budgets and balances at the centers. On the right, you see just an example of what that resolution looks like in the San Francisco Bay Area as we're looking at soil moisture on just one given day. Another very important data product that we use within CASI comes from the NASA sea level rise projection tools that you can see at sealevel.nasa.gov. There are a lot of amazing tools at that website, but allows us to look at many different climate models and scenarios, connect to specific tide gauge observations. That tool actually allows us to distinguish between contributions to sea level rise, including from different ice sheets and local land subsidence and elevation changes that could come from things like groundwater extraction, oil extraction, and even rebounds of the land surface from the last ice age compressions. As we're evaluating, of course, we are also moving beyond the hazards to think about the vulnerability and exposure. And here again, we have to think about the assets, the primary assets that we're trying to work to protect at each NASA centers. And of course, this begins with the workforce, but we are looking to protect NASA operations, the built infrastructure, the buildings and the facilities, in particular, the mission facilities like launch pads and test facilities. We're also especially interested in the energy and cooling systems in buildings and beyond, as well as the transportation infrastructure in and around the centers, and the ecosystems that in many cases go right across the center borders. So we want to think about things like coastal wetlands in some of our launch facilities and other very sensitive ecosystems right next to or even on the center grounds. And we're also looking at water resources that have broader expense, but also larger environmental ramifications. One example that we put together for the CASI project is a breakdown of the risk components for specific launch sites. So here we have a breakdown of different types of hazards that we're looking at. We have different types of exposure at these launch sites, including things like the roads to the sites, the employees that are working there, various cables and the launch pads themselves. We also look at the vulnerabilities, including proximity and low-lying land near the coast and the various thermal tolerance of built infrastructure. And when you pull these things together, you get a better idea of the overall risk and the potential response risk as we consider various interventions. We have to recognize, of course, that some climate adaptation or mitigation efforts could have costs, could lead to delays in the missions, could have some impact in the ecosystems as relocations occur, or as coasts are hardened, for example, that can affect the ecosystems that are no longer exposed or no longer connected to the marine environments that they had before. As we move to the assess part of the CASI project, we are going to now focus more and more on the actual projections of changing climate hazards and their connections to risk and potential adaptations. Once again, it's worth reminding that these NASA centers are very complex areas in very complex terrain. There's usually multiple acute and chronic risks challenging each center. And there are different threat levels given the different unique contexts from place to place, and even within centers, you can have very unique contexts. So this is why we need each of the CASI work groups, and we need to track the information as it relates to each center. Before we get to specific extremes, it's worth reminding ourselves that some of the background large-scale patterns of warming can be very influential and very challenging for the centers themselves. Here's just a map of the overall annual temperature change going out to the 2050s compared to a recent past from 1980 to 2020, here in the intermediate scenario across the 22 next GCMs that we use. You can see that there's slightly different warming rates at each of the different centers. We can also look at the overall sets of temperature change at a given center and how it relates to the various projection scenarios. On the left here, you can see that the temperature increase at Ames is going up in all cases, but at different paces, depending on the scenarios that are there. We also can see that the precipitation change is a much murkier picture. Different models and different scenarios have much more variance, much more variability. The trend is small compared to the overall variance, at least at this site. And we have to recognize that you get stronger pictures for some climatic impact drivers, for some hazards than for others. When we think about assessment of extreme weather, we can start with something like heat index and look at the Langley Research Center as a test case. Here we are looking at a heat index, which is a combination of extreme heat and humidity, which compound together to have substantial effects on outdoor workers, whether they're working on a launch pad or taking care of the grounds, or even waiting for a bus or a shuttle to get around campus. The ensemble mean projections for Langley indicate that more than 70 days per year will have a heat index that is classified as dangerous at Langley by the end of the century under the high emission scenario. So this is a substantial part of the season that is going to be seeing these high heat index events as we move further out down the century. And you can see here some measure of uncertainty because the climate models themselves have some disagreement related to local dynamics and the overall climate sensitivity of each model. Even under this low scenario, the SSP 1.2.6, there is still a dramatic increase in the number of extreme events that might come into play for Langley. When we're looking at examples from our CASI Energy Working Group, one of the things that they focused on was a set of building code zones related to the American Society of Heating, Refrigerating, and Air Conditioning Engineers, or ASHRAE. These zones were developed to describe the fundamental climate conditions for buildings with great implications for their energy use. In particular, there is a big interest in cooling degree days and heating degree days, as well as the annual precipitation and the average daily temperature. So these zones have different numbers that are represented here. And in general, lower numbers are warmer climates. By the calculations of the CASI Energy Working Group, the current ASHRAE climate zone for JPL, the Jet Propulsion Laboratory in California, is number 3, and under climate change, it will shift to number 2. That might seem like just a single number change, but for the ASHRAE standards, this requires or implies a strong motivation to shift a huge amount of building operations, and the construction of new buildings would have to recognize this climatic shift as thinking about walls and insulation and energy usage overall. It also affects lighting and the ventilation and air conditioning systems. Another type of energy analysis that we conducted at each center is illustrated here for the Goddard Space Flight Center in Maryland. On the left, you'll see the monthly change in the average number of cooling degree days, which is a measure of how much air conditioning might be needed. And on the right, you'll see a monthly change in the number of heating degree days, which is a measure of how much heating might be needed by an HVAC system. We present this under 3 different emission scenarios, with purple being the low emission scenario, so cooler or less warming, and the orange being the SSP 370, which is the high emission scenario with more warming. And as you can see, especially in that orange high emission scenario, there is a dramatic increase in the number of cooling degree days, especially in the summer months. That is much larger even than the changes that you see in the heating degree days over the course of the year. So there is an overall shift towards more cooling demand and in some cases higher overall costs in terms of the energy expenses. We also look in our fire and air quality working group using an index called the Fire Weather Index, which is calculated from a variety of meteorological variables, including both drought and wind type conditions. We calculated the Fire Weather Index and examined the entire continental United States. And you can see that some of the more fire-prone parts of the country where fire weather is increasing the most is in the southwest part of the United States. This is especially true towards the end of the century under the higher emission scenarios. When we look at both the Ames Research Center and the Jet Propulsion Laboratory in California, we see increasing fire weather index, with the Southern California Jet Propulsion Laboratory having an even higher fire weather index than Ames around the Bay Area. These conditions are something that could affect not only fire, but the smoke quality, air quality around the centers. The CASI Water Budget group has taken several different perspectives to understand the hydrology of each center. Here we're showing different perspectives of the Ames Research Center, especially around the takeoff and landing strips. What you'll see here is a detailed view of the land cover, the evapotranspiration water flux that happens in different parts of the grounds each year. There are examples where we have satellite-driven observations of surface inundation following heavy rainfall events, here taken from the Sentinel-1. And then we have strong classification of land and impervious cover classes for each part of the center to understand runoff, which allows us to model different types of water runoff around Moffett Field at Ames. So these different perspectives give us an idea of the overall energy and water interactions at different surfaces around the whole campus, the potential of flooding, both directly and as water runs off from key infrastructure. The CASI Sea Level Rise and Coastal Risks Group are taking several different approaches to understand coastal risks at each of the NASA centers. On the left, you'll see sea level rise scenarios for Bay Waveland, Mississippi, which is near the Stennis Space Center. And what you'll see here are different scenarios that are used throughout the US planning assessment that are developed by NOAA. And you can see these projections moving up. In this case, under the selected intermediate scenario, the sea level rise by 2100 is 4.29 feet compared to the year 2000. Not only do we see these scenarios, we see the contributions from vertical land motion, land water storage, the Antarctic and Greenland ice sheet, as well as glaciers and stereodynamic effects on the larger continental scale, rebounding from things like the Ice Age. On the right, you'll see a digital surface model from Wallops Island, which is a very highly detailed set of elevation information that can be used to understand how coastal floods might affect low-lying infrastructure. This gives us a 2-meter horizontal resolution and an accuracy within 10 centimeters. So we can use this information to really identify exposed places and compare their vulnerability and the future hazards that we're anticipating. When we take all of these work groups across all of the different centers, one thing that stands out is that there are different risks at different NASA centers. Even if we take the same set of information, we see strong differences across the centers. On the left, you'll have a plot showing on the x-axis the total annual heating degree days, and on the y-axis the total annual degree days. So in this upper left corner are places that need lots of cooling and not much heating, and in the bottom right corner are places that need lots of heating and not much cooling. You can see that over time, our projections are showing that each of these centers are migrating towards the upper left quadrant. That means they are moving from a situation requiring more heating to a situation requiring more cooling. And you can see how each of these centers follows their path. This suggests an overall shift of the burden from heating towards cooling at NASA centers. But of course, it's worth recognizing that they are still all in their own places, and in many cases, still in unique climate conditions that have to be recognized. In the right part of this slide, you'll see the increase in the annual number of extreme hot days that is apparent in nearly all of the NASA centers over the course of the 21st century under this intermediate SSP 2-4.5 scenario. The overall message of increasing extreme hot days is consistent, but of course, some centers are already experiencing more of those hot days today, and some are increasing very quickly towards the future. And you'll see this especially in the southwest and southern portions of the United States, where NASA centers in some cases can double or triple the number of extreme heat events that they will have to deal with. The other thing that's important to note is that there are multiple risks at many NASA centers. And here we'll take 4 slides to look at multiple risks at Ames Research Center in California. On the left, you'll see that the mean temperature is increasing regardless of scenario, with the highest increases under the SSP 370 high emission scenario. We developed models of air quality index as part of this assessment that show overall increases over time, reaching unhealthy conditions towards the end of the century. There is also a shift of energy load moving from the cold season where heating was a priority towards the warm season where cooling is a priority. So the overall change in heating degree days is shown on the left, and the increase in cooling degree days is shown on the right. Another risk at NASA Ames is the projected increase in extreme drought conditions. On the left, you'll see the increase in D4, which is an extreme drought category, as per the US Drought Monitor definition, which means less than 2% root zone soil moisture. This is projections from the SSP 2-4.5, or the intermediate emission scenario, and you can see this increase in the frequency of D4 drought events per year. We know that this is not just a water condition, it also relates to the thermodynamics, and this type of increase in drought is apparent even in some places where the precipitation and overall amount of water supply doesn't change so much, because as the mean temperature increases, there is a higher demand for evaporation and evapotranspiration, which can reduce the amount of available water in the soil, as you see in D4 increases on the left. NASA Ames also has projections showing increasing risk of flooding events, both from heavy rainfall. For example, on the left, you'll see some observations of how heavy rainfall has affected the facility in the past. There is also an increase in coastal flooding that is projected in the sea level rise scenarios for this region. And in particular, not only is the sea level going up, but you'll see a dramatic increase in the projected flooding days. In many cases, the episodic flooding events have a different pattern, and in many cases, a more nonlinear response than the sea level rise, the average sea level rise itself. And of course, that comes from flooding, from coastal flooding, including not only the mean sea level, but also the coastal surge, the waves, the run-up, and other conditions that can come along with a storm. Within CASI, we also have to emphasize that the emission scenario really matters. This is a look at extreme hot days at Goddard in Maryland, and you'll see that the future is highly dependent on the emissions trajectories and the emissions pathway that the world follows. Under the high emission scenario, extreme heat reaches more than 60 days per year by the end of the 21st century, whereas under the low emission scenarios shown in orange here, it barely reaches 30 and usually is below 30 days per year. This type of difference is owing to decisions that are made far beyond the center gate. So it's important to recognize that while NASA has a role to play in the overall mitigation challenge, mitigation beyond the center gate is still critical to addressing adaptation challenges. If we can reduce the overall level of hazard, meeting those adaptation needs will be easier. All right, for the implement and monitor, I'm going to turn back to Sanketa to describe how we did this within the CASI project.
Thanks, Alex. It's important to remember that CASI 2 is an ongoing initiative with continued conversations with our stakeholders. We've presented preliminary CASI results in this presentation. A more formal report is planned for early 2024. We're currently working with our partners to translate all of this information into actionable items. Adaptation decisions and planning is underway. We are humble about our role in this process. As is often the case, the scientific process does not dictate the planning timeline. But to see how CASI information may be useful, I wanted to give you an idea of decision mapping through the OSI divisions. Here is a flowchart of one. Under the Environmental Management Division, the decision areas are environmental cleanup and restoration, the natural resources risk management, the NASA NEPA compliance, and the NASA CRM, or the Cultural Resource Management Program, and the Greenhouse Gas Management Program. So now adding the CASI products into the picture, we see the linkages where these products could be used. So for example, the sea level rise and coastal flooding inundation product could be used in several of these decision areas, like the environmental cleanup restoration, as well as for the natural resource risk management decision areas. The important thing to remember is that one or a combination of products has linkages to more than one decision areas, as we saw, and each decision area benefits from more than one CASI scientific product. To address acute climate risks effectively, it's crucial to identify both reactive and proactive interventions tailored to specific vulnerabilities. In our planning, we recognize that success can be measured on multiple time horizons, from immediate relief to long-term resilience building. When evaluating interventions, we scope out their feasibility according to various factors such as cost, technical capabilities, the lifespan of the intervention, etc. So the personnel requirement is also a key consideration. It is essential to align interventions with existing rehabilitation cycles to maximize efficiency. Connecting to existing climate action plans or resilience plans or sustainability plans at the centers as well as at the agency has been an ongoing effort. Our findings are delivered through a variety of communication products like the annual reports to inform stakeholders about our progress and challenges. We are also working to find entry points into existing documentation like the NASA design standards that are used agency-wide. Adaptations are not general, but they are targeted and synergistic. CASI is now working on creating synergies and co-benefits between adaptation, mitigation, and other center priorities.
Pulling together all of this information across the CASI project, we wanted to highlight a few fundamental CASI findings. There are growing climate risks identified by each of the CASI working groups. The sea level rise and coastal flooding group has shown that sea level rise is strongly dependent on the emission scenario, with currently rare coastal flooding becoming increasingly normal as the century progresses. CASI's extreme climate events group has shown that there is an increase in the heat humidity events, heavy rainfall, drought, and extreme storms across many of the NASA centers. The CASI Fires and Air Quality Working Group has shown that there is a rising risk for wildfire and smoke impacts, particularly for the Western centers. The CASI Energy Working Group has shown that there is a decrease in seasonal heating and an increase in seasonal cooling loads. There is also a shift in the climate zones associated with building energy standards, the ASHRAE categories. The CASI Water Budget Group has shown that there is an increase in evaporative demand at all centers, even in some regions with increased rainfall. There is also an increased drought in many Western centers. When we examine CASI findings from an agency and center perspective, we note examples of growing climate risks across all centers. All centers are projected to experience increases in extreme heat with shifts from heating towards air conditioning expenses. Langley is projected to shift from the ASHRAE Climate Zone 3 to ASHRAE Climate Zone 2 in the 2060s under the high emission scenario. The Ames Research Center is projected to experience large increases in the frequency of moderate to unhealthy air quality conditions from fires after the late 2070s under the high emission scenario. The Goddard Space Flight Center is projected to experience a 38% increase in extreme inland flood days per year by 2100 under the intermediate scenario. Wallop's projections indicate that chronic flooding, here representing at least 50 days per year, becomes likely on an annual basis beginning in 2038 under NOAA's intermediate sea level rise scenario. Kennedy projections indicate that it is likely to see an increase in chronic coastal flooding beginning in the 2040s and has a 98% chance of at least 20 flooding days in a year by 2030. Johnson is projected to experience an increase in cooling degree days by at least 5% under the low emission scenario, by 9% under the intermediate emission scenario, and by 14% under the high emission scenario. As a whole, CASI is helping to provide targeted information to support climate decisions. CASI data and products are helping agency and center master planners incorporate climate risk information into ongoing planning processes. CASI is helping the agency understand the broad array of climate observations and modeling products that currently exist across broad domains, helping to translate those into CASI data, products, and support at the center level so that they can inform climate action plans, center resilience plans, agency resilience plans, and together help identify climate response actions that may be implemented in the agency master plan, the agency capital investment program plan, and the center master plans. This process is, of course, being conducted with coordination between the agency and center master planners to facilitate the connections. And the whole thing is part of an iterative process by which the demand from the implementation side is driving the shape of CASI products and ongoing research. This iterative process was demonstrated in the first phase of CASI and is continuing in the second phase. And there is the potential for continuing implementation and monitoring and reassessment as the years progress. The theoretical approach that we explained in part 1 of this ARSET training has helped CASI achieve decision support goals based upon an inclusive and comprehensive climate risk assessment. Across the 5 phases of our risk assessment approach, we have seen that the CASI approach allows climate information to be tailored to decision processes. It allows for contextual analysis in close collaboration with partners. It allows us to select climate products that match hazards that drive risk for key assets. It allows CASI to produce risk assessments and characterize uncertainty across models and scenarios. And finally, the CASI approach connects information with decisions in support of sustained scientific engagement and flexible adaptation pathways tailored for each center. As a summary of what we've done, CASI provides a portfolio of key current and future climate risk information for center managers and their regions. We have used this climate risk assessment methodology on the right to produce a series of products that are co-generated and linked to decisions protecting center assets, infrastructure, and workforce. Centers can therefore use this risk information to identify adaptation strategies for implementation and further planning. Thank you.
Thank you, Alex. As a reminder, there will be one homework assignment which you can access from the training page. Answers must be submitted by Google Form with a due date of October 5th. A certificate of completion will be awarded to those who attend all live webinars and complete the homework assignment by the deadline. You will receive a certificate via email approximately 2 months after completion of the course. Below is the contact information for Dr. Alex Ruane and Sanketa Kadam, along with links to the training webpage, website, and social media. We hope you will sign up on the ARSET listserv to receive notifications of future trainings and follow us on Twitter, now X, for other relevant announcements pertaining to NASA's Earth Sciences. We would like to acknowledge all the people on this slide for their contributions, as well as the rest of the CASI and ARSET team. The following slides are provided for you as reference materials, and we will now transition to the Q&A portion of today's webinar. Thanks. Excellent. And so far, we've gotten a lot of terrific questions. So again, if you have one, please do put it. It's not too late to add it to the question box, and we will get to them in the order that they were received. So jumping right into it, question number 1. Has CASI done these assessments for non-NASA organizations? This is an answer that Alex provided. So we have not done CASI assessments for non-NASA organizations. The CASI focuses on increasing NASA resiliency, but they are open to expanding and collaborating with non-NASA organizations. And the fundamental risk theory of identify, develop, assess, evaluate, etc., can be applied to non-NASA organizations as well. The NASA GIS Climate Impacts Group has worked on impacts for a large number of sectors and regions, including the New York City region, ecosystems from the Mesoamerican reef to snow leopards in high mountain Central Asia, and agricultural and food system risk in more than 20 countries around the world.
Yeah, just to say, CASI is one of many organizations also, of course, working on risk assessments around the world. And we have engaged with broader U.S. Global Change Research Program collaborations to think about risk more broadly within the U.S. government. And you know, and connected also with private sector folks interested in similar topics.
Okay, great. Question number 2. Is there a tutorial on which application I can use for the near real-time temperature data, and how can I download this temperature data?
So let's see, I didn't put this response here, but I would call in particular on some of the ARSET folks to help. ARSET is one of the best sources for training information and tutorials on how to use these data. So I might turn it back to you, Sean, if you know any off the top of your head that would be looking at temperature data. And in particular, I thought maybe something related to the NASA Disasters Program would be applicable here.
Yes, absolutely. We will put some links into this. I believe Sanketa answered this, but I did also provide that link to the Earth Data Search. There have been probably 4 or 5 different trainings where we've covered land surface temperature for MODIS spheres as well as Landsat missions. So we'll be sure to add those links to this question and answer document, and we will upload that to the training page by next week. So whoever asked that, we will have some more resources for you at that time. So question number 3, how accurate are downscaled products? What are various methods to do so? Which is the best among them?
So here we recommend watching the recording from last year's ARSET training on selecting climate projection sets for your particular application. The summary of that really is that there is no single best product that is always the go-to product, but it's helpful to use that ARSET training because we give some guidance on how to examine the strengths and weaknesses of each projection set according to these fundamental distinguishing characteristics. And we talked about that in today's presentation around CASI, you know, our need for different variables, our need for different scenarios, our desire for the latest models, a large number of them so we can get ensemble statistics, and our interest in bias adjusting to higher resolution so that we could get to some of the scales of the centers. These are the application of sets of guidance that we talked about in that last approach. Or that last ARSET training. But I do also just want to emphasize, as we did in the presentation, higher resolution is not always higher quality. And when we look at bias adjustment, we have to recognize that if you do that with the statistical approach, it will very well reproduce the statistics that you use as your target data set by mathematical definition. And that can be very useful. But it also means that if you move out of sample into new climate conditions, the statistics may break down. And there could also be challenges when there are physical mechanisms by which those small scale patterns can change. Just as a very simple example of this, when you go to high elevation regions, we see over and over again in the climate literature that high elevations are warming faster than low elevations. So if you apply the same elevational correction in the future and the past, or in the future that you observed in the past, then you would likely underestimate the warming at high elevations.
Great, thanks, Alex. Question number 4. This is a question pertaining to the Land Information System, or LIS, and this refers to, I guess, slide 41. I think you said revaluation being in there. So does that mean you combine the satellite data with ground data and some ground truthing to confirm?
So LIS is a amazing setup that utilizes multiple land models, and they have a setup that includes data assimilation when they were looking at historical period runs. So we sometimes call this retrospective analysis, and this allows us to connect all of the information that we can bring to bear. So that includes satellite data, ground data, other observational data sets, that allow us to constrain the physical models to reach a physically consistent simulation that closely represents or resembles the combined observations. So we know that there are some uncertainties and biases in each of the observations. We know that there's uncertainty and bias in our physical models, but when we combine the two, we can constrain the model biases by using observations, and we can rectify some of the observational uncertainties using the physical intuition that the model provides. And that also allows us to fill in some gaps, for example.
Great. Question number 5. Proximity to coast increases exposures, but socioeconomic limitation and dependencies increases the vulnerability. But why have we classified proximity to vulnerability?
So I believe this question was looking at a risk propeller type diagram where proximity to coast was put under the vulnerability propeller or propeller blade. And I tend to agree with the questioner. That's not very clear. Probably it makes more sense to classify that as a marker of exposure, but I'll use the question to also just re-emphasize the main point there, which is if you wanted to solve that problem, effectively what you're doing is saying, let's take this system and move it from the place where it will be affected. So that seems like you're reducing the exposure as opposed to hardening the system or creating some kind of engineering solution that makes it so that the system is not affected, which would be more like a vulnerability change. So vulnerability can be more than socioeconomic, it can also be engineering or biophysical, but the questioner makes a good point here that we could be more clear there.
Great, thanks, Alex. Question 6, how common is it to include hydrological variables like stream flow, overland runoff, groundwater recharge, and evapotranspiration besides the standard variables of precipitation, temperature, solar radiation, wind speed, and wind direction to inform climate zone maps at the county level? Would LIS be used in such cases?
So a couple interesting topics raised by this question. So there are actually a lot of operational systems that use hydrologic variables as their primary piece of information. So if you're interested in water resources, flood risks, water quality, other areas where hydrology is your main focus, that is the kind of thing that you would focus on those. LIS definitely helps inform many of these systems, but the second topic that I think is important to think about here is the idea of climate zone maps. There's a lot of different climate zones depending on who you ask, and sometimes they can be presented as the authoritative singular zones, but just in this presentation, you saw that we talked about the ARSET building zones. If anybody has a garden in the United States, you might know your plant hardiness zone. There are agroecological zones that are important in different parts of the world around fundamental decisions related to agriculture. And I'm sure we could go down this list, flood zones and other things like that. So I would push back a little bit about the idea that there should be a single set of climate zone maps, and instead kind of build on what the questioner is getting to here, which is that we need to design our zones around specific questions that are going to reflect the combination of variables that are most directly related to the decisions that we're making.
Okay, great. Question 7. How long does it take to complete an assessment? At the competition of the assessment, when is the assessment implemented, or how long does it take to see action?
So this again is very much a context and project specific set of questions or response, I guess, is what I would have to say. So we have been working within CASI for a while. You can see that the response here, CASI has been working for the last 2 years, and there's a general 5-year plan. If you recall, the last step is to implement and monitor. So we don't like to declare the project over when the climate is continuing to change. So there is a continuous need, and in that sense, it's hard to define a true timescale. The assessment itself, has a scientific set of activities that are undertaken. Many of the people working in CASI are working also on other projects. This is not a full-time job for each of us, so that also affects the timeline. Now, in terms of the implementation, as we mentioned at the end of the presentation today, we are providing scientific information into the master planning process, but we know that there is a lot of other pieces of information and competing motivations coming into this process. And we also know that the master planning process has its own time horizons and budgetary constraints that are connected to the financial side, but also the political side and other things, in terms of budget allocations from Congress and other things like that. So we can provide the information in, but the rate at which it is implemented gets far beyond the scientists' purview. And this is some of what we're seeing now. The information is clearly being used, and it is formally recognized as a key input to the master planning process. But the implementations are following the investment in rehabilitation and improvement cycles that are already ongoing.
Great. Question 8. Where can we get Python source code to make similar visualizations, for example, charts, anomalies, anomaly maps, etc.?
Sanketa, if you're available to answer this question, I might turn this towards you.
I was going to say that there's a lot of available Jupyter notebooks online that you can definitely look into, and there's other ARSET trainings that I might refer to Sean for, but I've given an example here. So Goddard has a Jupyter notebook for assessing fire risk, for example. So yeah, those were just some examples there.
Thanks. So we haven't, I don't think we've created like a public facing CASI scripts database yet.
No, we have not yet.
If there's interest in that, that's a further conversation. But for the most part, the types of plots we're making are utilizing fairly standard Python scripts and routines. So the types of plots that we're making, you can find examples of in the types of archives that Sanketa just mentioned.
Terrific. Question 9. The vertical land motion looks to be the most significant contributor to rising sea levels. Can you explain more about what vertical land motion is?
All right. So I would quibble with the idea that is the most significant contributor to rising sea levels. It depends where you are, and it also depends on which time scale you're looking. So there are places that have seen substantial resource extraction, water resources, oil resources, gas resources, where the land motion is certainly substantial. That includes some of the NASA facilities in the U.S. Gulf Coast region, for example. Another aspect, and maybe I should say that generally tends to cause the land to sink faster when you remove those underground resources. The other major aspect of land motion is the isostatic rebound from previous glacier ice age type ice sheet activity. So the fundamental idea is when those massive ice sheets, a mile thick ice sheets were over places like northern New England and much of the interior of North America, that was a lot of mass, and it compressed the continental plate in a way that is still rebounding. So there is still a slow expansion as the land decompresses from the ice that has long since melted. That rebound leads to a small amount of land motion, but because those ice sheets were largely in the northern parts of the continent, you also get a tipping plate type response, where the uplift at the northern parts of the continent as that plate kind of rebounds is leading to some parts in the southern part of the continent where it's actually tipping the plate downwards. So I don't know how to say this without waving my arms frantically, but the basic idea is if you have a plate that was pushed down in one place and it comes up, you're going to get the rebound on the other side of the plate as well. So we are tracking those things, and as you can imagine, there are parts of the continent that are moving up and down most or more than others. But in terms of the long-term aspect here, it really is the climate change influences on ice sheet melting, in particular in Greenland and Antarctica, where the most freshwater ice is kind of able to affect the system. We're seeing this very strongly across the world with IPCC measurements, or measurements, I should say, assessed by the IPCC. Glaciers all around the world are receding, and the ice sheets are destabilizing quite rapidly in many cases.
Great. Question 10. I know NOAA also does a lot of work related to sea level rise. For example, NOAA has an coastal inundation dashboard, and they provided that for us. How do you interact with NOAA for sea level rise issues in terms of synchronizing the assessment?
So Sanketa, it looks like you've started the answer here. Maybe you can give that response and I'll add.
Yeah, the web tool that we've created for CASI Center-specific sea level rise and coastal flooding data is developed by the same people that have worked on the NOAA interagency report that came out last year, the new one. So all of the information on the web tool and the data comes really from the same scientific assessment that goes into the NOAA website and reports as well.
And just to add to that, so sometimes you'll see this as the NASA sea level rise tool, but the scenarios are often the NOAA scenario. So there's close collaboration across those groups.
Great. Question 11. How do you include cyclones and the intensification of cyclones in the analysis?
So we have presented here some of these preliminary results. Our work groups include analysis of extreme storms. And that includes high winds and heavy rainfall. We know, for example, that the Johnson Center in Houston had substantial impacts from Hurricane Harvey. We know that coastal surge is a big concern on the East Coast and Gulf Coast facilities. So we are tracking those things. In general, climate information for tropical cyclones, including hurricanes around our part of the world, show a significant increase in the number of hurricanes that reach the most extreme categories, and show an intensification of the rainfall that does occur when the storms occur. The question around the frequency of those hurricanes and their tracks and the speed of propagation are all being investigated further within the scientific literature, but the messages are not nearly as clear. But this type of information is certainly being considered as CASI goes forward.
Great. Question 12. For climate adaptation, we need monitoring, evaluation, and learning. What methodological approaches do you recommend using at a national level? As it is at a national level, we are struggling to actually capture the impacts of implementation adaptation actions. We are working with a methodology that aggregates metrics in efficiency areas, but what do you recommend to capture progress that gathers local information and escalates it to a national level?
It sounds to me like we need a deeper conversation with this questioner. So that sounds like they're doing some interesting work I'd love to learn more about. But the fundamental idea here is we are in a unique setting within NASA that NASA has these facilities all around the country. So inside the agency, they have the ability to think about this on a national scale and on a center scale. And one of the goals behind CASI is to merge some of these efforts. So rather than each center being left to their own scientific assessment and planning strategies, by coordinating and collaborating, we are likely to have a better set of science and a more a smoother process to share best practices and findings. So similar things could be done in other places, but we you know, as I think the questioner is getting towards, there is more opportunity to track these projects, to link projects, and to learn from all of these projects, and also to understand the difference in scale. There are adaptations done from a personal level to a household or a community level, across urban and rural landscapes, and you know, even on like full city-wide levels. You know, a place like New York City is one of the biggest, you know, decision centers around in terms of the mayor being able to control or being able to influence so many assets and so many people and all of those things across a broad region. So tracking these adaptations around the country, I would agree, is a very interesting and important topic. I do think that there have been some efforts to promote or to facilitate or enable climate actions, both for adaptation and mitigation. And those are already leading to new initiatives and things like the Inflation Reduction Act, which included many climate activities. When there are subsidies, I know that those projects are being tracked carefully to try to gauge the overall impact. So as you can hear, this is a much longer conversation, but I would generally agree with the questioner that it is helpful to try to think about how to link these different projects. But to the very last point here around kind of methodologies here, it is important to recognize that the projects are highly contextual, and therefore there is a risk of trying to establish only a singular set of metrics or measures of success. And in many cases, it requires a deeper dialogue to figure out what's really happened.
Great, and if I can just address the questioner directly as well, there's going to be a survey as well as on the homework, which is now on the training page. There's actually two open-ended questions. They're more like just, you know, an open-ended answer that we're hoping to gauge some of the work that you all are doing in this area. And for the questioner that asked that, we would love to hear more from you. And you can find that on the homework, which is now on the training page, as well as in the survey that we'll be sending out early next week that also addresses some of these questions. We would love to hear from the community on some of the work that you all are doing. So yeah, please, for the questioner that just asked that, please do fill out that survey as well as the homework. So thank you. So question 13. What recommendation do you have for selecting risk guides? For example, the traditional use of the 100-year flood. Would you recommend the estimation of the 100-year flood for the end of the economic life of the structure or facility under consideration?
So again, the first answer I'll give you here is that the scientists can't make this determination on their own. This is a great example of importance, you know, of co-development. So what I would say as a scientist myself is, if you want to determine the risk level, let's talk about the lifespan of the structure or facility under consideration, as the questioner alludes to here. So if your structure is only going to last a year or two, you are playing with a different set of statistics than if your structure is meant to last 50 or 100 years. Of course, you know, if you've looked at probabilities and understand the definition of a 100-year flood, it does not mean that it happens exactly one time every 100 years. And it certainly does not mean that it won't happen until 100 years from now. We've seen many examples in recent years of events that people thought were 1 in 100-year storms happening multiple times in the same decade. That can happen by chance. It can also happen more frequently when the statistics themselves have changed. So one thing we talk about with the stakeholders is that the idea that the 1 in 100-year storm is something that we can clearly define and draw from statistics that go all the way back to the 1950s. That really is no longer the case. The climate is non-stationary. The distributions are changing. So we would want to ask questions, effectively saying, you know, rather than the 1 in 100-year flood, let's ask, you know, how much can that river rise before you run into problems? And if we look at the old statistics and say, well, that river level is associated with what used to be called a 1 in 100-year flood, well, that might lend itself to us looking at that return period. But even more importantly is that water level. And we might ask the question of, what is that water level in the future? Is it still a 1 in a 100-year storm, or has it become a 1 in a 20-year storm? At which point your statistics and your risk have changed. So part of what we want to do is we want to focus the conversation not on probabilistic statistics, but on some real thresholds of exposure and vulnerability.
Okay, great. Question 14. How much does it cost to produce the full CASI project and deliverables? Does this include a comprehensive risk assessment report to the NASA facility managers?
I certainly don't have an answer off the top of my head on the overall cost of the project. What I will say is it involves a small amount of time for representatives at many different centers. And that is, you know, you could break that up into budgets per center and get an idea of what that looks like. But again, I don't have the numbers off the top of my head. But what I can say is that in many cases, the collaborators are already working on the types of issues that we're talking about. So when we're talking to the facilities managers or the people who are doing their master planning, it's not new funding for them to work on climate. It's something that they're already considering and already working on. And what we have done here is provided better scientific information. Likewise, you know, many of the people who are working on this project, one of the reasons CASI was put together is in recognition of the expertise that NASA has in-house. So, you know, being able to bring in the power group at Langley, who is, you know, among the world's experts in understanding energy for buildings and photovoltaics and other things like that. You know, these are areas of research that we could do at a very cost-effective basis because we already have those experts working on similar topics. In terms of the final report, yes, we are presenting or producing comprehensive risk assessment reports, but really the goal of this project is not to produce a paper report that will be put on a shelf, but it is the stakeholder engagements at the end of this process that allow us to really relay the messages and have conversations about what it all means to the master planners and the Office of Strategic Infrastructure. So I'll leave it, I guess, with that as my best response.
Great, thanks, Alex. Question 15, what were the sources of future temperature projections?
In this case, we're using the outputs from the next global downscale daily product or projections, so the next GDDP. There are 34 global climate models from the latest CMIP6 climate model outputs, which are bias adjusted down to final resolutions. And we then take a subset of those climate models that pass some preliminary tests around their climate sensitivity to make sure that they are within the IPCC very likely assessed range. And that allows us to have a subset of about 22 models, I think. That is the core set of projections for CASI.
And last question, question 16. Why does California experience high wildfire risk even though most parts of the state are near a water body?
So California is very, very big. And even right next to the coast, you can run into issues because the direction of the weather patterns and the broader climate system of California is still a semi-arid kind of Mediterranean climate in the south. And in the northern parts, even in places that are not directly semi-arid, you have big mountains that can get the moisture out of the air, and you have deserts and semi-arid regions, depending on those mountain shadows and other things that can happen. So the bottom line is California is a semi-arid climate, and even with the ocean nearby, there is still huge. It would be hugely expensive to pipe ocean water into all of the places where there is currently high fire risk. Even then, ocean would not really be sufficient to pipe into the ecosystems to reduce the aridity because it's saltwater, and those kind of forests that have developed over the course of the last centuries and millennia are accustomed to the semi-arid climate. So I used to personally live in San Diego, and there was a wildfire that burned its way effectively across the northern part of the city to the sea. Being close to the ocean did not help the firefighters. That was a tremendous challenge, and the work continues to try to understand and prepare for the increasing fire risks.
Wonderful. We have effectively gotten through all of the questions. Thank you to everybody that posed a question in today and on Tuesday as well. These were absolutely terrific questions. So thank you again. We're going to post, we're going to clean this, edit this, provide some links, and put this on our training page. This should be uploaded to that training page by next week. Just a bit of housekeeping. Remember, there is one homework assignment. It is currently on the training page. So if you're interested in getting a certificate for attending this webinar series, you can access that currently on the training page with the due date of October 5th. And so thank you. And also, I also want to let everybody know there will be a survey going out early next week to everybody that took this webinar series. And we do please encourage you to complete that survey. It is absolutely invaluable to the ARSET team to be able to take that information that you're providing us so that we can make trainings more effective to you and all of the community that's interested in this application area. So as we wrap up, I did want to give an opportunity for both Sanketa and Alex to provide any closing reflective thoughts on this training. So maybe Sanketa, we can start with you.
Yeah, thanks. I just wanted to say that, again, thank you all for joining the training, and the questions were really amazing, and it helped us learn a lot more about your work as well. So yeah, I think this was just a great session for us.
Yeah, and I wanted to add, first of all, I see there's still about 250 people watch this presentation and the question session. So we really appreciate the interest. And hope that what you have seen today is something that you find interesting, but also potentially useful for your own activities and your own research or decision-making processes. Yeah, we continue to be interested in building out collaborations and hope that there will be a possibility to work with all of you down the road. Thank you.
Great, and we especially want to thank Dr. Alex Ruane, as well as Sanketa Kadam and Nick Palacio, all from the Goddard Institute for Space Studies. Thank you so much for leading this training, and we also want to thank all the participants that attended over both parts of this training. Thank you so much. We do hope that you'll submit the homework as well as the survey so that we can get that back. And I also want to acknowledge all of the ARSET team. That's Dr. Amita Mekta, Brock Blevins, Dr. Melanie Follett-Cook, Natasha Johnson-Griffin, and Selwyn Hudson-Odoy, and Sue Monty. So thank you to the ARSET team, and we look forward to seeing you at a future ARSET training. Thanks.